Monica.
Thank you so much for inviting me and hosting this lovely workshop. Today I'll talk about operator algebraic approach to understand the AdS CFT, and more specifically about the subregion duality. I'm going to include certain few parts about not just this paper, but it'll be mostly about this paper that I wrote with Jason Cran, who is a pure mathematician who have never even seen mathematical physics before. And so I'm not actually going to go over any of the proofs, but the proof is incredibly demanding analysis on algebra. So why do I care about the operator algebra? So I thought this is a very cheeky way to explain this, that I think we all really like Steven Weinberg, and in his this book, this is actually my favorite quote from him, and he actually really say that addressing looking into geometric interpretations, it's really powerful, and geometry has brought us a lot, and intuitively it's a great way to think about it, but it's not otherwise very useful in a way that to actually address it, to actually compute, it's not really that powerful. It's because analysis is really hard. And this is where the Sir Michael Atiyah comes in, who actually, this is also one of my favorite quotes from him. He actually really expressed that how algebra is so powerful. It's basically an offer made to devil to the mathematicians. So by expressing geometry into algebra so that we give up geometry and then reinterpret that into an algebraic paradigm, we can actually have this marvelous machine of algebra, and that's what I'm going to exactly do today. So the idea to think about it is that in quantum mechanics, you have the finite degrees of freedom, so you could count explicitly all the states. And we quickly learned that in quantum field theory, this is actually really difficult. We have now fields, infinite degrees of freedom, and this infinity really arises from short distance. So that if you recall back in the Planck type of formalism, we can then understand coming from two operators and put it in close distance, then quantum field theory actually told us that a particle then comes about and this paradigm in high frequency and short wavelength, and this is how we got quantum field theory. But this is not just for the quantum field theory, this will also work, and it can give rise to a particle that's gravity. So that in gravity, then we'll get the graviton and high energy, and this gives the quantum gravity aspect. So in this way, if you're phrasing everything in operator perspective, operator algebra is really the natural effective toolkit to understand the really quantum effect that we should be able to capture in this paradigm. So I like examples, and I like things very simple. So in quantum mechanics, back in like freshman in undergrad, we learned a simple harmonic oscillator, and this already highlights how powerful operator algebra is. So in that perspective, we first learned how to solve Schrödinger equation, which is, in my opinion, really annoying and difficult, because we in the end had to get the Hermite polynomial, and we had to do all this grotesque integration techniques and to get the actual answers out. And then we quickly learn after all, like, oh, forget about all that. We can actually just write with ladder operators, and raising and lowering operators satisfying just this simple commutation relation, which gives the duet algebra. And that operator algebra is actually simply enough, and you can span the full Hilbert space. So in that way of thinking is that the operators are powerful because operator algebra is inherently local, in a sense that the individual operators next to each other are just locally interacting to right next to each other as an algebraic operation. We don't care about the operator itself as local or non-local because algebra itself doesn't really care about that. And this is really the essence I want to say why operator algebra has been so powerful, and which enables all the things that I'm going to say throughout the talk today. Despite that, to actually prove those, you will need a heavy machinery of mathematics. So an operator algebra is then a notion of an invariant, not just covariant, invariant notion of a quantum field theory and the quantum gravity as well. Like in fields, it's not an invariant notion, but for example, the easiest thing you can think of is a causal commutativity. Since you can think of the two separate spatial-wise separated regions, then we know that they will completely commute, and because operators are separately located in that local neighborhood, and any algebra on its own will never really have to care about that, so that it already knows causal commutativity as its physical invariance. And in fact, it goes actually beyond just using these things, so that in turn, these really capture physical information without depending on specific field description or even just a specific local operator descriptions, because once again, algebra doesn't care about the locality in that way. And this is really essentially the one that's proposed by Gessler in the 70s. So let's think about it as a quantum fields into the operator algebra paradigm, which kind of uses a little bit of Weidmann formalism. So to begin with, we're just going to consider Minkowski space, so it's very simple. And from there, then quantum fields is essentially what people say is a G covariant causal operator valued tempered distribution. What it means is that it just have a positive energy representation. And from this, the symmetry G, we have a G, the dual invariant as dense subspace, which gives rise to actually a dense subset, and a Hilbert space in the end, which is endowed with a unique fixed state that's given rise coming from the sector. So that quantum fields are then described by the space of bounded and linear operators. So that's a function space. That's how we can describe that as for the all the spaces, and in turn, that's prescribed by the commutation relations, like the ones that we just looked at, like in simple harmonic oscillator, but just in the much more complicated lying function space. And that gives rise to the Hilbert space in the end. And it, of course, generates a star algebra very effectively through its function spaces, all the subsets. So while this is a lot of abstract machinery, I think an example is always illuminating. So let's go to the simplest thing possible. So I'm going to now give an example of the Klein-Gordon fields in 4D. So as you can see, that in the Klein-Gordon field description, all this heavy machinery of math actually gives exactly what we have seen in quantum field theory. So that we can actually get the exact mass shell, and you can get the Hilbert space exactly generated from this perspective. And we can get the operators, which is a creation and annihilation space, and we get that now as a function space generated distribution functional into the Hilbert space in the same sense, and we get the quantum fields, just given rise by the operators we had as creations. And this is precisely what we have seen in quantum mechanics. So what we really are doing is that operator algebra can generate everything like this, and it's very smart without even thinking about quantum field theory too hard. So in this talk, then I'm going to use this effective paradigm of operator algebra. And operator algebra will be given rise as von Neumann algebra, and sometimes a little bit less as a C-star algebra, but will generate von Neumann algebra in the end. And the simplest definition that I can give you for this is as a star algebra, you're still in quantum mechanics, that's commutant is mapping back to itself. And commutant means you're just having all the operators to commute on its own. So it's really the center of this algebra that it generates. An easy way to think about it is that in string theory and a lot of places, we always use complex spaces. And complex structure was the effective way how we actually generated a lot of things. But here, we don't really have a complex structure, so this is a real structure. And this is already stringent enough that's generating a lot of structure from this aspect as a way to think about it. And it's still endowed with a symplectic structure. Because of the commutant being mapped into itself, it has necessary ideals, and that give rise to symplectic structures. So these operators will be then the one that we're going to look into from both gravity perspective and the quantum field theory in the boundary perspective. And for both the boundary control field theory and the gravity theory and the AdS, we will have the operators. And here we have to think about the operator itself has the locality. And the local bulk operators will be not quite local boundary operators, so we'll have to deal with the smearings. They're going to be smeared over an entire spatial slice or a compact spatial subregion, so that we can actually deal with it, address it accordingly with the neighborhood, not just as a dot. And from those, we'll have to now put it in context. If you remember that every quantum field and generating into Hilbert space, we had to deal with what is a correct subset of the Hilbert space, and that's the notion of a subspace that rise about. And we have seen that coming rise in the our community, so that local bulk operators in this von Neumann algebra can give rise to code subspace like the ones that we have always looked into as the bulk space of the physical Hilbert space of the boundary control field theory. So that in turn, the important thing to think about is how we're going to now express from these operators into the states. So the first thing we need to then describe as a notion is a thermal state, which should be described by this something called KMS state. So I'm going to motivate this coming from what we already know from quantum mechanics. So consider a completely tame and kosher finite n-dimensional system. Then we have just linear algebra. So we can just write the full trace and everything and not to worry about any oddities. So we can write what we already know as a time evolution, and we get the Gibbs ensemble to get the thermal state. So generalizing this notion to now infinite dimensional space and to address all this quantum field theory is then dealing with how to make this possible. Like you don't really necessarily have a trace. You don't really understand how to make these possible. So how do we actually do that? And that will be the one that's what makes it KMS. And K and MS are coming from these two different papers, which is used similarly, but I'm going to use the notation of this for today. So reformulation means that we have an algebra. So it has to be at least C-star algebra, which is not very complicated notion. It's just a Banach algebra with an involution. And then so they can still have an adjoint. And so that's a more relaxed structure than the von Neumann algebra. Of course, von Neumann algebras satisfy this as well. So we need to have a state. So we need to have some amount of functional that give rise to an identity. And we have a continuous one parameter group of a star automorphism. This is the one that's effectively given rise to time evolution. And then thermal state can be given rise as this very explicit following. What it means that we can have an extension as an analytic continuation in this temperature or inverse temperature, so that you can write this accordingly with this continuation. So that now you can have a continuous parameter instead of being finite before and gives exactly the same thermal state. And you can actually truncate with this back to the finite dimensional system. You'll get exactly what you had to begin with. So then from there, a notion that is defined, this is actually one of the more modern notion from operator algebra from 90s by Inoue, called the KMS system. So what it requires is that you have now the algebra with the this subset as a subspace of the Hilbert space. This will be the code subspace you're going to deal with. And you have the this time evolution, and you have a cyclic vector, and then this KMS condition. Note that you don't need separating condition yet, because this will just give rise to that existence of a vacuum of cyclic separating state. For experts, if you have heard of operator algebra, you don't actually need this stringent notion. You can actually use an unbounded operator as well, but we're not going to use that today. So from here, then we need to describe the geometry, because the whole point was that then this algebra will describe our gravity space and replace the geometry. So the one way to think about it is that you can have now consider a wedge. So it's considered a right wedge, which you can write it very explicit from the GR, and you can have the Lorentz boost, and it can get the remained invariant. And while this was actually very demanding annoyance of a differential geometry proof to do this, you can actually do it very simply in algebra. Now you just consider all the polynomial algebra generated by all the field operators average over the test functions, the unitary representation we have, and the vacuum, which is a cyclic and separating state. If you have these, you can have now something called KMS system that we just went about, was this. And that just generates entire geometric modular action. It recreates entire this, even with the coordinate system together. So it's very powerful. It's a general version of this and completely in algebraic settings, so you can bypass all analysis. So I hope now that you're more convinced that operator algebra is actually powerful. Let's do something explicit nice. So one person that first used this is Bizanano Wickman. And in their proof, they explicitly address this type of system, while more preliminary than this, because of course, this is older than Inoue, the concept that I explained about. And it recreates all this. So they can have the anti-unitaries and modular operators to give rise to it, and you can have the boost generator, that's the modular Hamiltonian modular operator, and the edge reflection. And so from there, we can recreate the full cone and actually understand the entire GR accordingly. So it's actually as powerful as it gets. And once again, while I'm not going to address it, you can even work directly with the unbounded operator, so you don't actually need to even come up with a bounded set of von Neumann algebras. You can actually use this machinery and be done with it, which is very powerful. All right, so now I'll actually use these machineries of von Neumann algebras and C-star algebras in context holography directly. So to address von Neumann algebras, once again, you have to be a little bit going through a procedure, because von Neumann's algebras require only bounded operator sets. So for them, you need to now do the polar decomposition so that you can have some open region of a space-time. And then this is in this open compact region, so that in here you can define all the associated local operator algebra to be generically then on unbounded operators. So you need to then bound them so they can do the polar decomposition into a partial isometry and the self-adjoint positive operators. And you can do see that this is canonically associated with a set of projections by spectral theorem. So from there, now we can generate von Neumann algebra very explicitly by these all partial isometries and all the set of projections. And together, we can actually have now von Neumann algebras on that explicit open region of the space-time because while it itself is not local, it has a local neighborhood, so to understand where the region it came from. So that in turn, with this notion in mind, it's basically a way of thinking this KMS system with the correct distribution of this, where's my laser? In this wedge, you can write this and replace with any generic notion of open space-time, that's what it means. And you can even extend the open region of space-time and their wedge as well. So then with this in mind, let's look into the AdS CFT with that together. So what does AdS CFT tells us? So we could actually have that the AdS is a universal cover, and the boundary is then exactly the control boundary that we find. And in this notion, then the first question is, oh, this is a very different setting. Can we then address that what I was introducing from the Minkowski into AdS space? And this was done in early 2000s, so that you can write an explicit covariant operator value distributions in this AdS, and you can write the explicit KMS system, and it gives rise to explicit geometric modular action with the correct time. And this is done by these three gentlemen. And in that context, then let's actually look into how we're going to describe the individual fields. So in the AdS to CFT side, we always write that with this from the bulk. And from the boundary to the bulk, we need to use now the smearing function because otherwise we would not be able to go back from boundary and bulk because of the difference in locality of the operators. So then the natural question is then what is really the bulk dual of this boundary subregion, which is really the quantum gravity aspect that we couldn't have learned before, not just the metric. The first thing that we have learned is that from the RT and HRT that you can actually do something like this, but this is only possible in the finite dimensional Hilbert spaces because you're just doing the area over and over. Otherwise, you're going to have this divergence in the UV limit, and that's not what we want in the boundary CFT. So what did we actually then look into? Let's try to fix this in some ways, is that then we consider now the wedge that corresponds to this boundary region of this A. And then from there, it's diamond, so it's symmetric. And then from there, I think I started late, so. Wonderful. So this is the smearing function. Let's remember where the smearing function actually came from. So this is supported in this domain of this wedge of this A that it generates, and the domain of the A. And this is not really possible. You're not supposed to multiply distributions. No such thing is ever possible, even in analysis. So it has many issues. And the way to address that wonderful physicist that came about is that this is only valid on the subspace of the Hilbert space. This makes sense even mathematically, in a sense that because the bulk observables supported in this wedge of the A are encoded as operators protected from the erasure of the space-like complementary region from the domain, so that in turn you're truncating so that when you multiply singular region with a singular region, sometimes it works. And this is the beauty of the operator algebra sometimes, and this is what we're really kind of doing, yes. Yes. It's not a full region like this. We actually have to do the subspace. So this is the code subspace that Alm-Harry-Dong Harlow came about, or the code subspace is the bulk Hilbert space that in our context, but this will be generically true in any context that you would need to do, because once again, this multiplication of the distribution doesn't really work. And this is a way to make it work. While this is not mathematically done, it's basically it's a way to resolve that issue in the same sense. And actually, that mathematics was discovered already by Benny, Kempf, and Cripps by the operator algebra quantum error correction. If you apply this, you can make a mathematically rigorous proof that why this actually works, which is really fantastic. All right, so now then associate this operator algebras to the bulk and boundaries of two different theories separately, which is acting on individually infinite dimensional Hilbert spaces. Now let's actually look at what it can really generate. So this is a little schematic diagram how you can think of it. So you have all the boundary operators. You can have the region A and the complement of the A. So individually they will then generate the von Neumann algebras. Now the bulk region, so this is the corresponding region. It generates the actual entanglement wedge, which we'll get to. So then these will be the ones that generating as the von Neumann algebras of the operators lying here, and this is a commutant. And then you can have the isometry coming from this acting on this code subspace, which is the bulk, and to the physical space in the boundary. And this is the only input coming from physics. All the rest are really algebraic. And then from there, we're going to then make that the vacuum maps and preserved to be a vacuum between the two theories. And in that context, we can actually show explicitly that entangled wedge reconstruction can be written like this, as the operators coding from the bulk can exist coming from the something from the boundary, and then it maps exactly one another. And you can actually explicitly prove something like that is possible in the stringent condition that you have, like in free theory. Now, when you don't have free theory, you can now look into if you can then generate what we already know as entangled wedge reconstruction to relative entropy conservation. And then from here, can you generate something like an RT formula, not just working in the finite truncations, but also in beyond, in the algebraic conditions, and explicitly generate such a formula that we can have. And we can prove that this is explicitly equivalent without using through this, and then using there, we can derive a equation, something of the RT formula in turn. So to do that, we need to relax the relative entropy context, the thing that's very crudely learned that we could do in high school or undergrad. So this is like a measure of distinguishability. So we can generalize it as a notion that exactly gives rise to that. So this is something called relative modular operator. Which means it's relatively given between this and this. So that then this can be given rise by taking all the sequences of the operators to be well defined onto this state as a limit. And then that it actually, it has a commutant. And so that it means that you can actually generate like this. So it's modular completely. And this is the vacuum, and it's guaranteed to at least have one by Ryu-Takayanagi theorem. So that in turn, this is manifest. And if you put that back into the context of finite dimensions of type 1 in von Neumann algebra in turn, it actually spits exactly this back out. So from there, we first then showed that these two are actually equivalent. So the notion of the bulk reconstruction and the relative entropy to be exactly identical. If they're both exact, they're exactly equivalent under just one assumption of vacuums mapping back exactly to the vacuum in the boundary. So let's actually rephrase it very simply. So now with better notations, we can actually just simply write like the following. So you have code algebra, the physics algebra, and the subregions with the isometry. Then you can just make them to be correctable under this mappings under this isometry respectively, which give rise to the quantum channel between bulk and boundary. And for there, then we can have the vacuum as a cyclic and separating state to exist. So the relative entropy is equivalent on there, and it's commutant. And from there, we can explicitly write then what it can generate as the algebraic condition for these to be possible as a Ryu-Takayanagi type of formula. It only works on type 1 and 2, but it's not just type 1 finite. So it's a huge, I think, nice thing to do by Su and Zhang. It's pretty fresh. Definitely less than 1 year old. And approximate versions of these, which means that now you have to deal with the higher orders of G Newton, because these only work exact by the G Newton to 0. You can now do two different relaxed versions of approximate versions to include higher order gravity. And one way to deal with it is an n direct sum of type 1 factors to be generating higher orders, or being n is hyperfinite to address as asymptotically approaching the boundary. And I'm going to first explain this, and then this will be utilized right after. So in order to then do this, we need to give a notion beyond just the entangled wedge, which is called the reconstruction wedge. So that so the correction contains higher order of G Newton, so that we need to then do incorporate the jumping of the entangled wedges. This happens naturally, for example, when there's a black hole, so that there's a two-man zone. So it's an entangled wedge, and entangled wedge cannot be state dependent, so this actually cannot be possible. The reconstruction wedge is something that's omitting that. So dealing with this together as this red line's reconstruction wedge, and from the original entangled wedge is basically this two-man zone. And those things are now described by this reconstruction wedge. So then we have to be taking all the things that's only contained within after the entangled wedge jumping, so that we can take the intersections of all the entangled wedges generating with respect to all the mixed states in the code subspace. And you can generate that as a reconstruction wedge algebra. This actually takes a lot of heavy protocol of the upper algebra theory. If you're curious about how to explicitly do this using this reference state and modular approaches, you can talk to me after the talk. But this actually can work out very precisely. And the main difficulty you address is to make that work is that the standard notion of a distance between quantum channels is actually really hard, both the completely bounded norm or diamond norm, because of this explicit infinitely diverging understanding of the von Neumann algebras. And you can imagine any continuity going in diverging is difficult to have a distance. And the way to deal with that is then if you lose information disturbance trade-off, there is something to rescue you called privacy correctability correspondence. And then by using that, we're going to deal with complementary recovery. So we can deal with the complement region, and then by working onto that to move it back by using this basically information disturbance trade-off. And this privacy correctability correspondence were discovered by these four mathematicians, so that you can actually have this channel to be then private. So let's say it's epsilon private, then it's correctable by 2 square root of epsilon. Now if it's epsilon correctable, it's 8 square root of epsilon private for the complement. And you can see looping is not helpful. It's going to get worse and worse. So it's not actually good to loop around. Yes. Yes. Yeah. Right. So this is the vector representative generated by the von Neumann algebra that give rise to the state. Correct. It is not 0, especially when you have a black hole. It would not explicitly be 0. It would be explicitly non-zero, actually. You'll see the effect. No, they're not equivalent at all, because you're actually taking the intersection, and entangled wedges are going to actually jump around when that happens. It is identical up to G0, G Newton to the 0. That's your semiclassical representations, but this is a Stein-Spring dilation to include that, so meaning that you'll actually address the full. This is completely functional analytic, so it's not just algebraic. Very good. So from there, then let me then explain briefly then what actually private and correctable really means. Though I think the name itself is kind of quite telling. So what does it mean by private? The private means that you can have now an explicit channel, so that it's completely private means that you really get none. So that none of the information contained is accessible from the domain of this quantum channel. So then the exact setting that we looked into thus far is that this MA in this orange zone, that should have been orange, bad, with respect to then the complement that it generates in the boundary for the usual boundary to bulk map is exactly what we have seen. So then by relaxing this, you can have now epsilon amount of information is accessible. So you can have a channel doing that that's allowing the epsilon amount of information, so that in approximate, you're taking now this red instead as a reconstruction wedge, so that this epsilon is not necessarily 0. This is allowed to be now a certain value, which will generate with respect to the G Newton. Now, correctability means that you can have now a recovery channel that gives rise to exactly the reverse. So that what it means that in exact that the entangled wedge of this A and the where did my here this goes, there exists the exact star homomorphism that's mapping from the bulk algebra to this boundary algebra in this orange. Now, to relax that, then you can have now epsilon amount to be possible. So the recovery is not completely recovering, but it has also this. So that this is really the approximate possible. So in this context, what we can do is that now epsilon is non-perturbatively small. So this is the one that's generating some negative divided by Newton, G Newton. So it's generating all orders if possible. And from that this is shown to be equivalent so that you can have the relative entropy conservation, something that complicatedly generated all that together. As I was telling you, it's actually complicated proof that you can do this. But essentially, that's bounded by this epsilon. But in the recovery formula, so that you can actually do explicit recovery that you can do, you have the this amount to be out. It's epsilon to the 1/4. It's kind of interesting that the difference will be 1/4 G Newton. Kind of hints us something, but I'm not going to be able to deterministically say that's really the area over G Newton. But that's the difference that we get. So this actually generates up to all non-perturbative gravity aspects. Did I miss something? No. All right, so now this is also great, but we need to actually see the space-time aspect. We're not going to really address the full geometric description of the entangled wedge or this reconstruction wedge unless we can actually explicitly do that. So how about now we fix this complementary recovery type of things with the privacy correctability correspondence with the heavy machinery that we have built. And can we now look at it to see the entangled wedge directly or reconstruction wedge from this algebraic setup to actually can tell where this is going about in this aspect. And how we're going to do it is motivated by this nice physicist work to intertwine the kink transform with the Kahn's cocycle flow while keeping the complementary recovery formalism. So what is a Kahn's cocycle? So we can have now two states, and it's very nicely describing for the one of them. So it becomes so this is going to be the vacuum. Then the Kahn's cocycle is described by the one that's generating t as a modular time, which will become actual real time is really the idea here. And it generates like this with respect to that. So that the Kahn's cocycle of the two states in this von Neumann algebra will be always still within the von Neumann algebra. And this is not true in modular operator in general. So this is already hinting us something that it's remaining intact. So that the difference between the modular flows of two states is exactly the inner automorphism that it generates, which is necessary for us to actually address the gravity. So then, given a boundary region and the state, then what is really then the bulk geometry of this Kahn's cocycle flow? So what this Busso et al. Was saying is that in any asymptotic AdS, the bulk dual is the kink transform of the Ryu-Takayanagi surface is the conjecture that they have been proposing. So then can we actually prove this using operator algebra and quantum error correction perspective so we can actually generate a real spatial derivative in time? So that we can actually not only just see the entangled wedge, it requires us to actually generate not just modular time, a real space-time. So the kink transfer conjecture is that then we can have a bulk kink transform, which is a one-sided boost of initial data about the RT surface of the boundary cut. And on the boundary side will be the one we have the Kahn's cocycle flow. So how are we going to really prove this is that we apply the Vis-Nano-Wickman property together with the KMS system that I described this earlier for the Whiteman fields that it generates in the universal cover of the AdS. It actually requires a very sophisticated handling of modular structures and unbounded operators by the Inoue that I was briefly mentioning earlier because I need to really get into full KMS system data. But this is doable. We've explicitly done this. And you can actually see how it changes and it literally generates the kink. It's really marvelous. So this is actually for entangled wedges exact. So this cut that it has as this kink where it generates is an entangled wedge. So generic states. That's why you have to do unbounded operators. If it's a vacuum, you don't need to do that. And they will not be actually generating a real time. That will be modular time. That's a real difference. So spatial derivative, this is very technical. I'm just going to show that something like this is really possible. Let's actually describe what that really gives rise to. What it gives rise to is that you can really get the KMS system with the spatial derivative. Spatial derivative is really that this time it generates from the Kahn's cocycle flow becomes a real spatial-wise derivative that we can have in the space that we need to have so that we can actually generate the relative Tomita operator to be a very nice. And it's closing with the polar descriptions. And it gives rise to relative modular operator and the both this sense and it's this generated with the different type of omega states. So that in turn, you can have it not only just in the generic KMS state, but also to overall that it generates with the state with respect to. It's very important that this is omega and that's different. So in there, then relative entropy can be refined as a notion. This is actually the one coming from Araki into Inoue. So you keep this. I've kind of generalized it with respect to the this modular operator now has a reference. And then coming from there, you can actually exactly generate the relative entropy. It has, so I like examples. So let's go back to the simplest possible. So something that we actually know very well. Like we've put back to the semi-finite condition for this and with the everything nice all together. So it goes back to something like a finitely generated regular quantum field theory, regular quantum mechanics with the L1 norm. That you can actually recreate this. Doesn't that look exactly familiar? That's the rho log rho and rho log sigma. So it really recreates precisely back to that. And it has very nice properties, as you can see. It's explicitly generating nicely given rise to a norm. So that distance is definable. That's actually a big deal because otherwise you would not be able to actually compute these. And you can actually see that it can it has this automorphism that it gives rise to. So co-cycle derivatives is then can be given rise coming from this co-cycle flows as a spatial derivative, so that it gives rise to the partial isometry as a real time, that it generated this as a really additive feature with this co-cycle flow, and then it intertwines with the modular group. So it's not just a modular operator; it actually generates the time and prescribes a KMS to be always satisfied. So once again, let's then generate what this co-cycle derivative means in this semi-finite, like everything nice condition. Then it gives just rho it to the other state rho of minus it. This is what we have seen always before. So it really is the generalized version of this in this context. If you're curious on how to do that, it is in section 2 of the paper. It does use heavy machinery, but it's absolutely doable. All right, so with all that together, we actually show explicitly that the King transformation is exactly the bulk co-cycle flow. And we can, as a byproduct, get the full spatial derivative in nature. So you don't have to rely on modular operators. You actually get the real space-time in this operator algebraic perspective. So that it's no longer just something of the slice or anything. You can actually address now full thing. So then can you use this as a now correctability through this co-cycle derivative, derive the full space-time version of the theorem, so they can actually look into the exact and approximate recovery very precisely while having this explicit visualization to see where that comes from. So we prove this. So this is a first thing that we actually did is that we can now generate this explicit constant co-cycle flow to give rise to the an exact, given rise to the entropies, and all these three are equivalent. And a direct corollary, which I think is very interesting, is that we get emergent type 3-1 algebra. So if the boundary CFT this in subregion is a type 3-1, and the state that it generates, so this is a vacuum, onto this is ergodic. Ergodic means that your fixed point algebra is C1. So C1 is just identities and all the scalar multiplets of the identities. Where's my laser? So if you have that, there's only two options. I mean, this is what we always have in general in the CFT. So this is our expectation. Then the bulk algebra is either C1, so it's one-dimensional on its own itself, which is really sick theory, or it has to be type 3-1 necessarily. So as a subregion duality, it really instates that something like this is possible, and looking into this is very interesting. It kind of hints and echoes something like a baby universes, but I don't know yet. Yes? The boundary subalgebra. The full algebra, so this is everything in subregion duality, because all this full is much easier. Full, yes. If you use every possible operators together and all bounded operator set, that's always type 1. Yes. But if you do that, you're never going to see the wedge, so, you know, yeah. Yeah, so that's very interesting. You're looking into them, or if you don't know anything yet. So let's now go to asymptotic case. So it would be really nice to be able to do full asymptotic, like what I addressed earlier, but that's mission impossible. There are a lot of mathematical difficulties to address that, but we can do the asymptotically isometric, which is the other one that I haven't talked about, which is basically a notion studied by Faulkner and Lee. It's really where you reach the kind of like a large n limit is a way to think about it. So that in the bulk Hilbert space is fixed, and there's a sequence in respect to n in the boundary that pushes outward, and then you're taking this n to infinite. It's really the large n limit. And remark that I want to make is that this is really exactly the setting that can do very precise with the Whiteman theories, and you can look into them and compute it very, very precisely as the setting that you can do. So we prove this. This is actually even harder proof that you have to do. This uses something of a notion called ultra product, which is actually a notion. It's a notion to be defined in 2010. This is why my awesome mathematician collaborator was very, very essential in this program. So we actually show that the 3 is basically a relaxed version of the 1. So 1 implies 2, 2 implies 3. So that this is exactly the channels you can have with respect to this n. And then, so this is the recovery, and then this is the one that you can do with the Kahn's cocycle flow as a spatial derivative. And then from there, we can actually get the this 1's relaxed version back on its own. And when B is hyperfinite, which is the one that's dealing with the sub-Hilbert space of the boundary, then all these conditions are equivalent. It's because the 3 and 1 is equivalent. It's shown that 3 and 1 are equivalent in the Faulkner paper, but this is shown in a completely different sense because this one's using in this more generic. It uses less restrictions. And one thing that's probably too complicated, but I want to really mention that's something that I think is very insightful, is that now using all this machinery is all this theorem explicit use from the geometric modular structures. One of the things that we could very explicit prove is that we're using this operator algebraic subregion duality. I mean, not by using, we can prove that this is really holding and all accurate for between the boundary causal diamonds, which actually forms a boundary CFT. And how we cannot pinpoint what the CFT is because it's a dimension-free argument here. But we can show that it really necessarily has to be conformal field theory because the local nets are conformal structured. And the bulk causal wedges for the Klein-Gordon fields in the universal cover of the AdS. So that AdS CFT as a subregion duality is manifestly always true, and all of them are working if this is the case. It's a one way to, I think, a proof for the easiest setting they can think of for this type of argument. So today I went over the infinite dimensional holography where it is right now. So I addressed the exact recovery and then approximate recovery to be framed in the operator algebra format after motivating the why operator algebra is really this powerful and can really generate all the quantum field theory toolkit. And from there, I showed that how this is equivalent or is directly related with the bounds with the exact or approximate relative entropy conservation. And we even proved this using that to be doable in the space-time aspect so that we can look into the, Kahn's cocycle flow to generate a Kahn's derivative to be given as a spatial derivative, that we can actually generate this in space-time very precisely. So that we can actually have the everything done in the spacetime to see the entangled wedge. You can actually see the kink and how it really comes about to be really sourced by the Kahn's cocycle flow. While now this is very, in my opinion, awesome and great, while we are seeing the whole thing, we can actually detect the explicit curvature to be computable. So showing that it has this explicit kink and how it looks about is different from how we actually see the real differential geometric way of seeing the explicit differences to describe that very precisely. For that, we need to prove certain theorems in the PDE sense we do not know how to do, so you haven't done that. But that's will be very interesting to look into. And I think I did fast enough to make it on time. I think we're good. And thank you for listening. I'll be happy to answer any questions. Mm-hmm.
Matrices? What is the...
But not this one, right?
Yeah, exactly. What would be the analog with time dependence?
So this t is a time dependence and t is going into all real variable.
Oh, I see.
Yeah,
I see.
so this is really the flow that's generating in real time.
I see.
Yes.
Are you assuming the KMS condition is still valid?
So KMS is given explicitly coming from here.
Okay.
Yeah, this contains the KMS requirement.
Okay, thanks.
Yeah. Well, it's not an assumption that's needed. It's generating because of the requirement, how I defined it earlier, like in this fashion. So this kind of requires that because of this support is a projection of the state.
Okay.
Yeah.
Yeah, so I guess at this point you introduced this notion of spatial derivatives, which is
Like
a
this
little
one
bit
or
more.
this one?
Yeah, this one. Yeah.
The
Which is a
one I
little bit more
skipped.
technical than maybe you would usually use. So what was the exact reason for like going to this kind of formalism, like when
Because
you want
I
to describe
wanted-
this realistic time?
Because the modular time is great, but it doesn't really generate to where we really need to see. And due
That's
to
right.
the fact that operator algebra is really good at not just Euclidean Lorentzian picture, everything's Lorentzianly generating possible here. And from that perspective, then we need to actually see the real time because that's the limitation of the operator algebra before. And it was really doable by doing this type of notion. I'm coining certain establishments by these two, and then certain part is invented by my collaborator. And from here, it's very actually important that we generate this Renyi state of something that we can actually do. And this is like a way to think about it is that in 3D TQFT, it was easy to define a concept of a core and its commutativity. And can you do something like that when you lost completely complex structure, which is a real structure that can only have in Minkowski time or AdS. And this is basically a way to reinstate something like that is possible. It's like, I think, intuitive how you should think about it. I know I kind of skipped this slide because this takes usually 10 minutes.
I just wondering because I thought this was like a formalism you could use when you're not dealing with like normal states, but like more like weights, I guess. So
Correct.
yeah.
Correct.
So you're dealing with like some more general notion of a
That's
state,
correct.
I guess.
It's a more generally all states. That's
Yeah.
why you needed it. Yes.
Okay. Thank you.
Are there more questions? So we meet in half an hour.